Hello again guys, and welcome to another OrCAD X how-to video. My name is Adam, and this is the first of what I believe is 4 videos this month for how to create footprints from scratch in OrCAD X Presto. Now, I know that in a lot of cases, it's now a lot easier to find footprints on things like our third-party library providers. You can also find a lot of footprints just online. Maybe you already have a library of footprints that you can use, but every once in a while, you will get to a case where there is a footprint that you don't have, can't find, and you just have to take the time to create one from scratch. So let's take a look at what that looks like in Presto. And for this example, we are going to be creating the SOIC 14-pin footprint. So what I have here is the data sheet, which I found from Texas Instruments. As you can see, it's a 14-pin component. It's this nice SOIC package, very classic, very simple. And the nice thing is that in this data sheet, we get this package outline and dimensions on this page. This is page 60 here. If we scroll down, we have an example board layout that shows us the exact dimensions and even the radius of this chamfer here. So it gives us the exact dimensions of the pads that we should be creating. It also gives us dimensions of how to define our solder mask expansion around the pin. And finally, on the last page here, we also have an example of, how we should be creating our solder paste on each of the pins. So we'll go through and create this part from scratch using this as a reference. If there's anything that I am referencing specifically from these, hopefully in editing we'll be able to have it pop up on the screen for you guys. But for now, I'm going to move it off onto my second monitor. Hopefully, if you guys are a PCB designer or a budding PCB designer, I very much recommend having a second monitor for looking at data sheets, cross-probing between a schematic and a layout, etc. All right, so let's just jump into it. To create a footprint in Presto, it's super easy. It's File, New, Footprint. And what I recommend, the first thing that you do right after you create a footprint is go to File, Save As, and save it in your workspace. Now your workspace, if you remember, is where you keep all of the required documents and symbols, footprints, etc. for the components and projects in your OrCAD X Cloud workspace. So you can see that by default, this has actually placed it in my installation directory tools bin. Not a great idea to have all of my footprints and pad stacks, etc. in there. So what I'm going to do is navigate over to my workspace, CS setup, workspace. So I happen to know that it is in this location. Press enter, and we're going to go into my libraries, footprints. And here you can see that I already have a bunch of DRA footprints that I've created before. So what we want to call this is 14-SOIC. We want to change the directory so that this becomes our active directory, meaning that as we add things like pad stacks, they will all get placed into this directory. And just go ahead and click Save. All right, so the first step we want to take is we want to actually add some pins to our footprint. Again, 2 ways to do this, as you'll often find with OrCAD X. There's a couple different ways to do things. One is we can add pin using search, meaning that if we've already created a pin which matches the dimensions which are specified by the data sheet, we can then reuse that pin maybe between SOIC footprints. Maybe you're reusing pins between like a 0603 capacitor and an 0603 resistor, whatever it might be. If you've created it before, feel free to reuse it. But in this case, if we right click on here, we also have these options of the Add Pad Wizard, as well as using the tried and true pad stack editor. Now the Add Pad Wizard, you can either have it floating or actually no, this one is only floating at this time. Basically allows us to very quickly create a pad, which will then create a pad stack file for us and place it in that same directory. And here you can see we can pick things like, what is the shape of it, right? Rounded rectangle. What is the dimensions, right? Your width of the pad, the height of the pad, your solder mask and paste expansion, what is the corner radius, etc. Simply type in a pad stack name and then click Save and Add. Very simple. If you are just creating a footprint really quickly, this is what I would recommend. Now, if you have any other more complex requirements, what we do also have here is the good and old tried and true pad stack editor. Now, pad stack editor might look a little intimidating at first, but I promise it is really not that difficult, especially if you're making simple pads. The basics of it is that you go from left to right, starting from this Start tab, and then work your way all the way to the summary, and you save your pad stack, and then you can simply just close pad stack editor and forget about it. Now, what we're creating in this case is an SMD pin, and it is this rounded rectangle shape. And since it's an SMD pin, you'll notice that things like the secondary drill, drill symbol, drill offset, all of those tabs just got grayed out, right? We're not going to have any additional drills on this pad. If you, for some reason, need a drill on your SMD pad, we do have that option, but again, probably not. And then what you want to do is go into the design layers. So in the design layers, this is where we create our pad geometry. First thing I will also do before I start typing that in is double check what the units are in my data sheet, which is in millimeters. So I'll go ahead and change my units for my pad stack down here on the left to millimeters. And then what we want to do is click on this regular pad here, choose the geometry to be rounded rectangle, and then type in our width and height, which happen to be 1.55 millimeters by 0.6 millimeters. And then the corner radius, again from the data sheet, is 0.05 millimeters. Super simple, right? Now, thermal pad, anti-pad, keep out, those are for more complex requirements in pads. We're just creating a super simple surface mount pad, so we can just stick to having this regular pad on the top layer and move on to the mask layers. Now, if we look at our datasheet again, we know that the solder mask top layer is going to be pretty much exactly the same, except that it has an extra 0.07 padding on both sides. So what that means is we need to, instead of 1.55 millimeters, we want to change it to 1.69 millimeter width, and the height, instead of 0.6 millimeter, we want it to be 0.74 millimeters. The corner radius, simply just add the radius, so 0.5 plus 0.7 would be, 0.05 plus 0.07 is 0.12. And here you can check if you want the corners to be, on the top left, top right, bottom right. And then finally, let's go ahead and add a paste mask layer. Looking at the datasheet, it looks to be exactly the same size as our original pad. So you can either rewrite this information here, or if we go back to our design layer, copy this and paste it in our paste mask top layer. Now, if you're working with a pad for like a rigid flex circuit, you might have, cover lay layers. Any additional layers that you might need to find are in here. If you're working with a through hole component, which we'll do in another video, then you'll have some drill things that you might need to edit, or in the design layers, you'll have some adjacent internal default layers that you can set. But at this point, we just look at our options, look at our summary, and click File, Save As, and name our pad. Now, I like to use kind of a weird naming convention. So here you'll notice that I have, for example, these rectangles, rounded rectangles, and then I basically just say what the width is, say what the height is, and finish off with the the file extension. So we're going to call this a rounded rectangle with a width of 1.55 millimeters by a height of 0.6 millimeters, and then go ahead and save that pad, close pad stack editor, and then you'll see that our pad is now hovering on our mouse here. So looking at the options in the left or right side of the tool here, we see that we can add, for example, what type of pad it is, whether it's electrical or mechanical, the add mode if we're adding an array of pins or if we're just adding one pin at a time. And then we can do things like how much we want to rotate the pin by, what pin number we want to start with as we start incrementally adding these along the outside. And then if we have to increment by more than one, we can change that increment and so on. Now for now, I'm just going to place one pin just so we have it, finish with the command, just so that we have it placed on our canvas. What I'm going to do before we just start placing pins is actually look at the pin pitch and the spacing and adjust our grid accordingly. So if I look at my grid here, or if I look at my data sheet, there is this nice little indicator here that shows us that the pin pitch is 1.27 millimeters and the spacing between the left side of the pins and the right side of the pins is 5.4 millimeters. So what I'm going to do is go into, well, first thing, I want to change my design units to millimeters. Then we'll go into grids and set the X grid to 5.4 millimeters divided by 2, which is 2.7. And then the Y grid, we want that to be our pitch, which is 1.27 millimeters. Now, if you're working with a odd number of pins on either side of the package, then you will have to divide that Y grid in two so that you can fit a grid space between two pins. But in this case, we only have 7 pins on the left side, 7 pins on the right side. So 1.27 millimeters on the Y grid is plenty. So I can either take this first pin that I created earlier and move it simply to one of these grid points. I personally like to just start off from the first pin. So we'll go into our add pin using search. And we're searching for the rounded rectangle. And I remember that is 1.55 millimeter by 0.6. There it is. Simply click on it. And then we want to start with our pin number 1 and start placing it. So now that if I place my pin number 1 here, then we have pin number 2, 3, 4, 5, 6, 7, which should be nice and symmetrical. So 1, 2, 3, 4, 5, 6, 7. And then I can place pins 8, 9, 10, 11, 12, 13, 14. Now, instead of clicking each time, we also have these options of, for example, making an array, and then you can choose what the spacing is. So for example, we said that the spacing in the Y direction was 1.27 millimeters. And let's say that there's 7 pins that we need to add. Then if I were to click here, you'll notice that it incremented, it looks like in mils. But either way, what it does is it adds that array of pins for you rather than having to click each time on one of those grid spaces. I personally prefer to use the little grid spaces. I've been creating so many footprints in the past that's just what I got used to. But if you have a preferred method, go ahead and stick to that. Okay, so we have our pins placed. The next thing that we need to do is to add a couple different outlines that are specific to all components in OrCAD X Presto. And then we also need to add a reference designator on the silkscreen layer and on the assembly layer. All right, so first thing I'm going to do is actually change my grid back to something a little more usable, just so that I can draw an outline of the component on this footprint. Now, looking at my datasheet here, it looks like the component is about 8.6 or 8.75. I'm going to use 8.6 since it's easier to draw, millimeters in height. So let's click our, not our add connect tool, we want our add line tool. We want it to be in the straight line mode, and we want to use the silkscreen layer and do it on silkscreen top. And let's just make sure that we change our color here for silkscreen top to white, just so it's a little easier to recognize. And again, because our component is 8.6 millimeters tall, we're going to go ahead and measure out 8.6, so 4.3 millimeters, and that's where we're going to draw our line. Now, if we look at the bottom right here, we get a nice little indicator of what the grid point is that we're starting to draw at. And if we look at our snapping, you'll see that we are, I believe, snapping to grid points here. Oh, that's for object snapping. Yeah, so we are snapping to grid points. So if I hover over this point, even if it says in the bottom right 4.3017, it'll snap to 4.3. And then we can draw that straight line. And same thing on this side, negative 4.3, we can draw a line, which would be this one right here. Click and click. And the other thing I want to do is to also add an angled line here. And that's just going to be this nice little indicator for what direction the pin is to be placed in. And maybe we can even add a little pin 1 indicator on this pin 1 here using, for example, the rectangle tool. Let's put that on the silkscreen top, and we want it to be filled. And I like to, let's say, put it right here. There we go. So there's a nice little pin 1 indicator. We now have a nice outline on the silkscreen. Let's go ahead and add our 2 mechanical layers, which are the assembly layer and also the DFA layer. So to do that, I'm going to use our rectangle command, except this time I just want it to be a polygon, not filled. And if we go into components, you'll notice that we have this assembly top and bottom layer. And if we scroll down, we have this place bound top and bottom, as well as the DFA top and bottom. So those are, sorry, not the 4 layers, but the 6 layers, or 3 layers if you only care about the top, that we need to set here. For assembly, I like to use the entire outline of a component, including its pins. So looking at the data sheet, it should be 6 millimeters wide by, again, let's use that 8.6. So we'll go out to 3 millimeters in the X direction, which is right here, and should stick to our 4.3 on the height. And let's go ahead and just create our shape right here. Might have to turn off our selection filter. Yep, there we go. So we can start to create a polygon, right? Oh, I'm sorry. Rectangle is what we wanted, but we wanted unfilled. All right, so we want to start from this point right here, which is -3, 4.3, and go down to here, which should be 3, -4.3. There we go. Or roughly around there. I believe if I look at this point, it's exactly 4.25, which to me is close enough. If you guys want to be super exact, you can as well. But for example, I can go to the grids, set it to in the Y direction to 4.3, oops, sorry, X direction to 3 and Y direction 4.3. And then we can set it to exactly that size. So let's go ahead and do that. There we go. All right. So there is our assembly outline. And I believe we want to also possibly, let me check here. Nope, we're good. Okay, so there's our assembly outline. Now, you can either redraw this exact shape for your DFA and placebound. However, for the design for assembly, for the placebound, let's start with the design for assembly. So for the design for assembly layer, I'm going to use the exact same outline here, and I'll talk about the reason for it in a second. And for the placebound, I will use the outline kind of everything that we've drawn here. So let's look at the placebound layer, placebound top, and I want to snap to nope, this snapping is good. Let's just change our grid to something a little more manageable. And I want to go kind of as far as everything in this footprint. So maybe even 1 point farther out, like right here. And include everything in the footprint, just like that. All right, let's change our colors really quick for the DFA and assembly layers. So, all right, so DFA top, we want that to be, let's say, pink. And the placebound layer, we want that to be bluish. And our assembly top, it's already kind of turquoise, so let's keep it at that. All right, let's talk about why we want these different layers to be shaped as they are. So let's start with if we turn everything off except for our top pads and our DFA. So DFA is called the Design for Assembly layer, and it basically encapsulates the whole component so that when we're looking at our Design for Assembly spacing, we can measure from the bounds of a DFA shape to the bounds of another DFA shape. Now, specifically for assembly, when you're assembling with a manufacturer, they will specify a restriction, for example, that no components can be any closer than 3 millimeters away from each other. Now, when you're measuring those components, they're talking about the physical component that's placed on the pads, not the actual copper pads, but the component itself. So what we've done is we've outlined the shape of the component, including the pins, and then that component will be measured against the outline of another component to see if we're meeting those DFA rules. Now, something like the place bound is simply used for making sure that we're not placing parts too close to each other, right? It's kind of a redundant check, but it's looking to make sure that, for example, all of these pads and this component and everything to do with this component is not too close to another component. And those can be kind of your own arbitrary rules, or maybe you have a standard that you're keeping to. But either way, it's encapsulating everything that is to do with this component. Finally, we also have the assembly, and this is simply just a rectangle that you can then use on, for example, like an assembly drawing to kind of let a designer know where the component is placed. You can get a lot more creative with the assembly layer as well if you want to show, the outline of the package itself and then draw each individual pin. That's a little too time consuming for this video, so. All right, one last thing to add is our reference designator, and then we'll add the 3D body and we'll be all done with this part. To add the reference designator, simply click on this add ref des command, type in the reference, which is going to be U question mark, and then choose which layers to add it to. So silkscreen and assembly, go ahead and click OK. And you can hide these layers. In this case, I just want to see the assembly text and the silkscreen text. So there it is. And then you can change the text block if you need it to be a little larger, as well as this one. Let's say text block 3. Let's go ahead and just move that over to the top left corner for the silkscreen and the center of our part for the assembly layer. All right, now adding a 3D model is also super simple. Let's go ahead and jump into the 3D view for our component and turn off our, we want only 3D models. Now on the right side here in the properties, there's a section for a 3D model, which we can click this plus to browse our computer for a component. Let me go ahead and really quickly look through here for a 3D model. I believe I should have one downloaded. All right, so I have a 3D model in my C drive under temp Cadence, and there is my step model. So the step model, go ahead and just click open. And OrCAD X Presto is actually really smart at identifying how the model should be placed on your footprint. It does some really neat tricks to identify, for example, things that might be pins, things that might be your package body. But if for some reason it's not correctly placed on your footprint, what you can do is use these offsets here to, for example, offset the X direction by, let's say 5 millimeters, and that will move it in the X direction by 5 millimeters. You can rotate in each direction rotate around each of the axes, or you can simply click auto and try to have it auto place for you. In this case, it looks like when I click the auto that it's just a little off, probably because of this pin 1 indicator. So what I'll do is, see here, the Y got changed to 0.1875. So I'll just go ahead and change that back to 0, and our 3D model is placed. The good thing is you don't have to keep this 3D model in your workspace, because once you place it in your footprint, it actually becomes embedded within the footprint file. So from there, let's go back and switch to our 2D view again, and we're pretty much good to go. So we're gonna go ahead and hit File, Save, hit Yes. And one thing I just wanna show you guys really quickly is that when you save, let me get to my library here. When you save that, and we'll go into our libraries, footprints, and we're looking for the 14 SOIC. One thing that you should check is make sure that you create the DRA save file, and also you want this PSM file, which is basically just like a packaged or compiled version of the footprint, which is what actually gets used when you place that on your board. Alrighty, hope you guys enjoyed that video. This was us creating just a simple 14-pin SOIC footprint. In the next video, we're going to look at some time-saving features, or maybe even create some non-standard footprints, maybe some complex connectors with some weird pads. Again, hope you guys enjoyed this video. As usual, please leave a comment below if you have any questions, comments, concerns. If you have ideas for future videos, you can leave those below as well. Thanks for watching, guys, and see you in the next video.